name is Thom. I'm the Vice President of Software and Cloud Services at D-Wave. I've been with the company a little over 18 years, and I'm primarily involved in our software side, our lead cloud services, and our quantum application environment.
So for 18 years, may I ask, when was D-Wave founded?
D-Wave was founded in 1999 by two graduate students at the University of British Columbia, and I joined with the company just a couple of years after that, 2002.
I'd like to dive right into this. When the whole COVID pandemic situation exploded 1 year ago, you launched an initiative, like you opened up your platform for research, COVID-related research. Could you mention a couple of examples of the outcome? What came out of that?
Yeah, absolutely. Early on in the pandemic, we, like everyone else, were sort of learning about it and focusing on adapting. We'd actually been having some conversations with the Canadian government, who had asked private industry to open up the resources that they have available to others who were developing solutions in response to the pandemic. And we, like many others, decided to act quickly and do that. So we actually created an opportunity for people to sign up and get free unlimited access to our quantum computers and our hybrid solvers for them to be able to build and deploy applications that could be used with quantum hybrid compute technology. We did that. That was available to all of our users and open source developers in 35 countries. And we also partnered with organizations like Denso, an auto parts manufacturer in Japan, Jülich Supercomputing Center, MDR, Volkswagen, Menton, and Sigma I to basically not only help them to be able to build responses to COVID-19 challenges, but also so that they could work with developers and forward-thinking businesses who were looking to adapt the technology and see if it could help them. So we kind of created that developer community, those who were experienced programming on quantum hybrid technology and those who had a need associated with the challenges from the pandemic. Two interesting projects arose out of that, amongst a variety of different projects that people worked on. Sigma I out of Japan developed a variety of formulations for taking challenges to do with logistics and optimization that arise from the pandemic. And formulate them for quantum hybrid resources, including ones which basically looked at the optimization challenge of assigning patients to hospitals, knowing sort of like how many resources the hospitals have available and what's the distance between the patients and the hospitals that they need to visit. And they also developed other ones associated with helping businesses to be able to adapt a new normal scheduler for their employees who had to work partly remotely and partly in the office. Another company, Menton AI, has been developing protein therapeutics. These are proteins that are designed, they're like brand new designs for tackling challenges associated with medical therapeutics. And they do this not by taking existing proteins that are used in these contexts and modifying them, but rather by designing them amino acid by amino acid. And they were able to use our quantum hybrid technology to design proteins. They got them computationally validated with protein folding, chemically synthesized, and there are now quantum hybrid designed proteins that are out in live virus testing against COVID-19 in the wet lab.
Why is it that your platform is uniquely suited for that?
So it's sort of a question of what are the challenges with programming so many applications that are facing the world today? So like a lot of I think developers and businesses, you're looking at an application and trying to figure out, okay, how do you basically map the business problem that you're trying to solve to the computational resource that you have for tackling it. And when you want to, basically, for the developer, you want to do that in the most natural way possible, where you're really taking the real representation of the world problem into how you're tackling it with your computer program. Some of features of like everyday life, features where you have to make decisions and optimization. I need to purchase this or not. I need to select this entity to participate in my solution. Those events either happen or they don't happen. They're discrete. They don't happen, if someone joins your team to play like a hockey game, you don't get 10% of them on your team. They're either playing on the ice or they're not playing on the ice. That discreteness actually makes it a challenging problem for a classical computer to optimize. And even more so, like many things in our life, they're interrelated. So these choices about where patients are going to be going to hospitals, each of these individual choices affects the subsequent choices that are going to be made in that optimization. That feature of discrete choices that are interrelated makes these problems very challenging to solve with classical computers. And at D-Wave, with our LEAP platform, we've developed hybrid solvers which excel at optimization problems like this.
You're using a technique called quantum annealing, right?
Yes.
What exactly is that?
So quantum annealing is an approach to use quantum mechanical properties to help you solve a problem. I think the most commonly when people are talking about, what is a quantum computer, people will tell you, okay, we've got this idea. We want to leverage quantum mechanics for computation. We're going to take the fundamental building block of a regular computer and just modify it slightly so that now it can have quantum mechanical properties. Instead of just being in a 0 state or 1 state, it can be in both states simultaneously. And a lot of developers are sort of wondering, okay, well, how am I going to make use of a variable that's in 2 states at the same time when I'm trying to solve a problem? And the notion of quantum annealing is to effectively use that superposition to allow you to search a solution space. So a developer will say, here's a problem I'm trying to solve. Here's an optimization challenge that's stated from our application space. And we need to look through a variety of different solutions in order to be able to find one that is optimal for the problem we're trying to solve. In that scenario, the quantum annealer is effectively doing this process where it turns up the quantum properties of the computer, and that actually causes it to search a solution space by spreading itself out very broadly with the solution space. And that solution space can be larger than the estimated number of particles in the universe. That's what that ability will have. And then slowly turning down that quantum annealing and sort of relocalizing towards the best possible solutions. Very much as if you were thinking about this in a classical system, it would be like you'd move to high temperature and then you'd gradually turn the temperature down, like we have with thermal annealing. In quantum annealing, you turn up the quantum search and then you gradually tune that down, allowing it to localize to the highest quality solutions. And it being able to be in multiple places at once, to be able to move between those solution spaces quickly, all the quantum properties it has there basically reinforce the task of finding those high quality solutions.
To me, this sounds like pure science fiction, but you have been around for a little bit more than 20 years. Could you tell me about the history of quantum computing?
Yeah, absolutely. I mean, quantum computing is something that I think we all want to sort of get a bit of an idea around. So imagine taking ourselves back to the 1980s, where people were using computers to try to solve an expanding variety of complex tasks facing society at that time. There were quantum physicists back then who were trying to simulate quantum properties and quantum materials with computers, and they found there's no way we're going to be able to do this. Not only could they not do it in the 80s, they knew they were never going to be able to do it because quantum properties require such a huge number, an exponential amount of classical resources that it was always going to be out of their reach. And they said, if we actually built computers to harness those quantum properties, this would all of a sudden become possible. And Richard Feynman really popularized that idea in 1982. In 1994, Peter Shor, building on some of those ideas, said, it's possible to write algorithms with computers that had access to these quantum properties to solve some really important problems like factoring numbers, which is actually the basis of all of our sort of encryption mechanisms that we use as we're transferring information around over the internet. And that protocol really got a lot of people interested in quantum computing. And in 1998, some researchers at Tokyo Tech proposed an idea for taking optimization problems, which were being approached by a technique called thermal annealing, where you would move through a solution space with like high energy, accepting lower quality solutions, and then gradually reduce that temperature so you kind of settle down to high quality solutions. And they said, if that concept of thermal annealing is helpful for solving problems, we could actually do that with quantum annealing and give it quantum properties and help that search for solutions. 1 year later, in the United States, a group of researchers actually demonstrated with quantum materials they could do both thermal annealing and quantum annealing, and they were able to demonstrate at large scales with no error correction that quantum annealing did in fact accelerate the obtaining high quality solutions and low energy configurations of these sort of optimization challenges. So since that time, D-Wave has been building effectively a programmable version of that. A version which basically allows us to use traditional fabrication techniques to build devices that we can control so that we can create sort of connections from common optimization problems, like the ones associated with allocating resources or optimizing and designing proteins, putting them into a programmable quantum system where its quantum properties allow it to very quickly work its way to high quality solutions. And that's sort of like quantum computing over the last 40 years in sort of a quick snapshot. And that approach is key for practical quantum computing. Because, although some of the original need came from quantum physicists who wanted to discover sort of quantum material properties, the larger, broader impact is our ability to leverage those quantum effects for optimization challenges facing business in finance and manufacturing and logistics, as well as in the pharmaceutical industries.
And you've been mentioning big numbers, complexity, huge magnitudes. But still, quantum computing is very, very energy efficient. Isn't that right? How can that be?
Yeah, in fact, I have some quantum computers actually sitting next to me right here, and you can see the computer chip up in the monitor I have next to me. So one of the fantastic features about the quantum computers that we're building is that the actual metals that are used to print the circuitry on the chip are made so that when you cool them down to a really low temperature, they can superconduct, which means they can conduct electricity with no loss whatsoever. So when you think about like the computer chips that are in our phones or in our laptops, their operating temperature is room temperature, and when you turn them on, there's resistance in them. They heat up, they warm up, and then you have to like use a lot of energy that's going into that heat, and then use a lot of energy to pull that heat away so they don't overheat. In the quantum computer case, the operating temperature is very low, but when you turn them on, they don't heat up because they can flow these currents with no resistance. So while you have, let's say, like a refrigeration system, which just uses a constant amount of heat, no matter which quantum computer you're using, the quantum processor itself, the one that I have in the picture above me, uses 1/10 of a millionth of a watt. And it has actually been that level as we've been progressing through different processor generations. So as we are growing the scale and our ability to handle complex problems with quantum annealers and quantum computers, we're not actually having to scale up the power requirements of the system. And that's a transformative change in terms of high performance compute, because typically when we're using computers at a larger expanding scale, as our society is using computers much more broadly in an automated way, it has huge power consumption requirements. In fact, there are power plants set up to supply power to data centers. And these new technologies could fundamentally change that, where we could offset big portions of the computational tasks to a technology which consumes virtually no power.
So what you're saying is that once we have cooled down that environment, I could add another chip. So I would not even double, but multiply my computing power with a huge factor without spending more energy.
Yeah, I mean, think about it from the perspective that like over the last 70 years, the levels of integration on our classical computing chips has been increasing exponentially each year. And with quantum computing, we're actually able to leverage many of those same fabrication techniques. So at D-Wave, over the last 15 years, we've been doubling the size of our quantum processors every sort of 18 months to 2 years. That's an exponential growth in the size of the quantum processor. But what's interesting is that the problem itself is growing exponentially with its size. So the performance opportunity here is sort of like a super exponential growth. It's something that's quite dramatic. And if you have that scenario where you take one processor and then you double it in size, the computation for a classical computer can become square as complex. However many steps it did, you have to like multiply that number of steps by itself to then tackle that new larger task with a classical computer. So that can mean a huge growth in terms of the classical compute you need to tackle that problem, and a corresponding growth in terms of the power consumption needs. Whereas the quantum system that the quantum computer chip is in, you've taken one chip and then you've just doubled it in size. It becomes much more powerful in terms of the problem complexity it can deal with, but its power consumption has effectively remained flat.
So where do you see this going over the next 10 years?
Well, that's a great question. I mean, what do they say? Those who gaze into crystal balls are destined to eat broken glass. But quantum computing technology is going to allow us to take problems which are beyond our reach. They're even beyond our imagination with classical computers, and bring them into the realm of the possible. So that, although we've seen so much scaling in terms of computational resources in the last 10 years that have allowed us to open up into so many new areas, many of us are still familiar with some challenges that have remained inaccessible. Challenges associated with, really effective pattern recognition, or the ability to do like really high quality like personalized medicine. And also, basic logistics problems, scheduling teacher schedules in a school, or scheduling nurses in a hospital, allocating resources in response to a pandemic. Those, even at small scales, remain very challenging for our society. And that's because the nature of the problem themselves requires optimization over discrete variables that are interacting with one another. And so in the next 10 years, I think what that's going to allow is that, as our ability to solve problems in that space becomes much stronger, we're not going to need to sort of like approximate these problems anymore. We're not necessarily going to need to reformulate them into something that's better suited to our computational resources. Our new computational resources are now going to be well adapted to the more natural problem. So I'm hoping that things associated with like really high efficiency, like business and logistics operations, things where like airline schedules become simpler and easier to run, and the costs associated with logistics of a business in terms of like delivery schedules, vehicle routing, those types of things become really easy. And so in some sense, it will become easier to use these technologies in like everyday tasks, even the ones that are extraordinarily complex. I don't know if that's the right way of thinking, like what might become possible, but those are some thoughts on that space.
But all of this is in fact possible today. So how can I, as a developer, how can I benefit from your platform? How can I join your community today? Yeah,
well, I'm really glad you asked me that. So for developers and forward-thinking businesses who are excited about the prospect of quantum computing, and they're looking at how do I begin writing quantum hybrid applications, you can actually just search D-Wave Leap or D-Wave Cloud or D-Wave Applications and find a link to our Leap Cloud platform. Anyone can sign up right now. We have plans as low as $0. You can get in and have a month of free access, run some of the interactive demos, and go through some of the open source examples to see how applications can be mapped to quantum hybrid resources to build applications. We have a community portal with users who are experienced with programming the systems, and they're actually posting questions and responses to one another to help people as they're building applications. And a help center, which actually does a search over all of our documentation and information online about how to use quantum hybrid resources for building applications. And we even have an integrated developer environment right in that cloud platform to make it really easy to program the system. And if you are building an application that you are interested and willing to open source, we'll actually renew that access every month afterwards. And for those businesses who are not interested in open sourcing their projects, but they're actually looking to build businesses around what is now becoming possible with quantum computing technology, we've got plans that allow you to get subscription access that are on those business-to-business terms.
Which programming languages do you support with your platform?
So we have an open source software development kit called Ocean. It's written in Python. It's actually a combination of Python and C++ in order to be able to make the programming really easy and accessible for Python programmers, but it also has components which are written efficiently for some of the more computationally intensive tasks. And developers can find that we have our tools open sourced. We've got a set of D-Wave examples open sourced with documentation around them. Those are things that you can then load into our cloud services quantum application environment and begin programming in an IDE right in your browser to help you get started, so that you can find examples that are the closest to the applications that you have in mind, load them, review them, look at their references, and then start modifying them and importing your data so that you can get a quantum application built quite quickly.
And do we have debug facilities like in any other IDE? How rich is the environment here?
Yeah, so it's a fully featured integrated developer environment, and we've actually added extensions which integrated into our cloud service so that you can easily move back and forth between the resources that you have available in our cloud services and the developer environment itself. It's based on Thea. You can enter into debug mode and actually enter into the code. We've also got extensions to our libraries which allow you to dig in, and you can actually see the quantum machine instructions that are being submitted, inspect the sort of instruction that's being sent, as well as the data format of the answer coming back. But also, I think a lot of developers are really interested in, what can we build quickly with this system? So we have hybrid solver services. These are services that will actually deploy computers in the cloud and start working across the problem that you're solving with the best of classical and quantum computing technology. So it will actually break the pieces out of the problem and submit them to the quantum computer for you. And that allows developers to work with problems up to like a 1 million variable scale, really getting up to full scale for quantum application development. And I think, though, we don't want to divorce developers from the actual excitement of the underlying technology. So we also have features which would allow you in the developer environment is that you can look at those calls to the quantum computer and actually visualize them. And you can see the connection between the problem that you submitted and the actual instruction that went to the quantum processor graphically in front of you, and explore them as well as the set of solutions that you got back from the quantum processor. So I think it's going to be, it's a combination between the utility, the function of getting something done, and also the form of, seeing an exciting interface, learning about it, and really getting a chance to interact with quantum computing technology and programmable quantum systems very early on in that development process.
I know that you have recently published some research paper in Nature Communications. Could you tell me what was that about?
So that work was done in collaboration between D-Wave and researchers at Google. And we were looking at simulating a quantum material where its properties were occurring because of quantum mechanics. So it actually entered into a new phase because it had quantum mechanical properties. It actually affected the way this quantum magnet was working. And we, in the study, we both did the experiments using the quantum annealer as well as some really optimized classical code, which is sort of the best alternative way for solving that problem. And in that research study, they were able to demonstrate that it was 3 million times faster to do that with the quantum computer than it was with the classical techniques. And what's really significant about that is that is an advantage that has been demonstrated on a problem which is an example of like a practical application problem. Material simulation is one of the applications that people are really excited about with quantum computing. So that's along the path of developing quantum computing. That is one of the milestone markers of the development of the systems and their capabilities today.
So that kind of ties into the original thoughts from the early 80s, right?
Yeah, absolutely. In fact, many of the origins associated with quantum computing were, can we build computers that will allow us to simulate the properties of quantum systems? Because it was known that with classical computing technology, the resources you would need would grow exponentially as those quantum systems become larger in size, the ones that you want to study. So this really actually creates a connection to an early lecture that Richard Feynman gave, popularizing the idea of quantum computing, through to a set of researchers at Tokyo Tech who proposed ways of using these optimization heuristics and modifying them to incorporate quantum effects that were then demonstrated in the United States in 1999 And so, we have basically now gone from those early demonstrations that large-scale quantum systems using quantum annealing can accelerate calculations to a programmable quantum annealing system, which we can now use in those applications and demonstrate that advantage.
Thank you. This has been amazing. Thanks for joining us today.
Thank you, Preben. It's great to talk to you.